In the rectangular coordinate system, objects can move in one of two directions. They can move horizontally, left or negative x-axis, or right in the direction of positive x-axis, or they can move vertically, upward for the positive y, or downward in the negative y. We call these translations. We're moving the function. We're translating the function from one place to another. So horizontal translation, just like our horizon where we can see the sun rise, horizontal translation is left and right, and vertical translation is up or down. We'll talk about vertical and horizontal translation graphically and then move symbolically. And remember, the symbolic is related to what we do to the ordered pairs. That's how we end up with that symbolic notation. So to translate a point vertically, because we're going up or down, we change its y-coordinate, but we leave the x-coordinate unchanged. So if we were shifting the point A, B upward by the amount k, we add k to the y-coordinate. Let's look first at shifting the graph upward 2 units and label the points with the coordinates. I'm going to leave the labeling to you, but we will work through the shifting together. Okay, so upward 2 units means we take that point and we move it up 2 units and create a new point. Every point on the graph gets moved up 2 units in order to get translated vertically. If we do part B, downward 1 unit, starting with the original point, go down 1, and there we have it shifted downward 1 unit. Pretty spiffy little shape here. If we shift it up 1 unit, we take all of these end points, move them up 1 unit, and then we connect the dots in the same pattern that they are connected in our original graph. Similarly, downward 3 units, original graph, shift everything down 3 units, and we connect the dots in the same way as the original shape. So again, translation, we're just picking the graph up and moving it. To start out, we're moving it up or down only. I'll let you try 3 on your own. Let's see if you can move this absolute value function around as specified. And let's look at vertical translation symbolically. If we're adding or subtracting to the y-coordinates by a fixed amount, remember that y is f of x, so we're just going to add or subtract a number on the end. We just tack it on the end, and that allows us to create symbolically our vertical translations. We're adding k, the amount that we're shifting, or subtracting k, to y. And remember, y is just another way to say f of x. So an example, f of x is 2x minus 3. It's to be shifted upward by 4. So we add 4 to the function, the new function f of x plus 4, 2x minus 3 plus 4. Simplify it, we end up with 2x plus 1 as our new function. Some examples symbolically. We have our function 4 minus 5x. We're shifting down 3 units. 4 minus 5x minus 3. The downward 3 units. And we can simplify it. 4 minus 3 is 1. 1 minus 5 of x is our shifted function. In part B, absolute value function, we're shifting upward 1 unit. X plus 1. Up 1 unit. And we really can't simplify this in any way, so our shifted function will just be absolute value of x plus 1. Similarly for C, square root x, upward 2 units means we're going to add 2 on the end, and we cannot simplify it any further. Problem number 2 here says write the symbolic expression that represents the stated vertical shift, make a table of values 4 to 5, values for the shifted function, and then sketch the graph for the shifted function. Label the points on the graph with their coordinates. Here we're shifting 1/2 x minus 1 upward 2 units. So the idea is we just add 2 at the end. 1/2 x minus 1 plus 2. We're adding 2 at the end for that upward shift of 2. And when we simplify it, 1/2 x plus 1 becomes our new function. And we can put 0 in there. Plugging in 0 will give us back 1. Let's pick some numbers that have factors of 2. so that we can cancel with that 1/2. Negative 2 times 1/2 is negative 1. Negative 1 plus 1 is 0. 2 times 1/2 is 1. 1 plus 1 is 2. 4 times 1/2 is 2. 2 plus 1 is 3. And sure enough, noticing that we're taking these points and shifting them up 2, we get a new line, a new linear function. I'll leave B for you to try on your own. And 3, see if you can figure out from F to G, how did they shift? What's the direction? How much? So for part A, we'll do this one together. F is shifted up to G. If I take this one end point here, 1, 2, 3, direction is up. The amount of shift is 3. And the reason that we decided that, the G function is 3 units above the F function always. Here's a little more backtracking for you. F of x and its vertically shifted version G of x are given. We have to determine the direction and the amount of the vertical shift. Give a reason for your decision. So F of x is 3x minus 5. G of x is 3x plus 1. Since we had minus 5 and now we're at plus 1, we went up. How much did we go up by? Well, take new minus old. We went up by 6. And we know it's up because if I take this function and I add 6 to it, 3x minus 5 plus 6, we end up with 3x plus 1, which is our function g that's given. Try B on your own. Let's talk about horizontal translation. Shifting a graph horizontally works in the same way as shifting vertically, only this time we change its x coordinates, shifting them either to the left or the right, but leaving the y coordinate changed. So just like before, let's work some ordered pairs. We're going to shift right 2 units. So my original points to the right 2 units. Part B is left 1 unit. So we're going back to that original function. And we go left 1 unit, left 1, and left 1. We've got a triangle here, not a rectangle. Typos. We can play the same game as before. Shift right 2 units. So we take the endpoint, right 2 units, 1, 2, and then we can connect our dots, and we end up with our shifted, horizontally shifted triangle. Think about the absolute value function, what it means to shift right 3 units or to shift left 2 units. For horizontal shifts, things are a little different when we're talking about how to get symbolically our new function. So we have a function f of x equals 2x minus 1 graphed. We're told to physically shift the graph 2 units to the right by shifting points on the graph. So 2 units to the right, and we end up with this nice linear function. Fill in the table of values below for the original function, and as indicated in the right-hand column, give the coordinates of the shifted points. So here, -1 for x, y equals 2x minus 1, we get -3, so we have 2 ordered pairs there. The shifted coordinates, be careful, they don't go matching up with the x values in the table, so just be careful and mindful of that. If I plug in 0, I'll get -1, 0, -1, and we'll have our ordered pairs there. But now we deliberately, on purpose, make a mistake. Vertical shift upward is accomplished by adding a quantity to x. Vertical shift downward is subtracting a quantity from x. It seems reasonable that they should work in the same way, but turns out they don't. 2x plus 4 minus 1. We're going to shift 2 units to the right. Work through this part of the packet as far as getting a better understanding of horizontal translations. Read through the next part and see if you can figure out what's going on with the horizontal shifting and why it's not right. And we'll discuss that in the next class.